Good morning. Today's lecture is titled Neuroplasticity and Cognitive Reserve: Implications for Healthy Aging. I want to begin by revisiting a concept you should now be familiar with, neuroplasticity, and then introduce a related but distinct concept that has become central to contemporary aging research: cognitive reserve. For most of the 20th century, the prevailing view in neuroscience was that the adult brain was essentially static. Once the developmental period of childhood and adolescence was complete, the brain was thought to be fixed, incapable of meaningful structural change. This view was fundamentally challenged by the experimental work of Marion Diamond at the University of California, Berkeley. Diamond's studies demonstrated that rats raised in enriched environments with toys, social companions, and regular novel stimuli developed measurably thicker cerebral cortices and denser synaptic networks than rats raised in deprived conditions. Crucially, these effects were observed not only in young animals, but also in middle-aged and elderly rats, overturning the assumption that plasticity was confined to early development. The concept of cognitive reserve builds on this foundation. The term was first proposed in the late 1980s following a puzzling clinical observation. Researchers conducting post-mortem examinations of deceased patients found that some individuals who had shown no signs of cognitive impairment during their lives had in fact sustained extensive neurological damage of the kind typically associated with advanced Alzheimer's disease. The question was, how had these individuals continued to function normally despite such significant pathology? The proposed answer was cognitive reserve, the idea that certain individuals develop a neurological buffer that allows the brain to tolerate damage without manifesting clinical symptoms. This buffer is thought to arise from the accumulation of dense, redundant neural networks over a lifetime of cognitive engagement. When primary pathways are damaged, the brain can recruit alternative routes, maintaining function even as the underlying pathology progresses. What factors build cognitive reserve? Research consistently identifies three. The first is educational attainment. Individuals with more years of formal education show greater reserve. The second is occupational complexity. People whose careers involve high levels of problem solving, decision making, and information management develop stronger reserve than those in less demanding roles. The third, and perhaps most actionable, is sustained intellectual engagement throughout life. Activities such as learning a second language, playing a musical instrument, or maintaining an active social life have all been associated with a delayed onset of dementia symptoms. It is essential to understand what cognitive reserve does and does not do. It does not prevent neurodegeneration. Post-mortem studies consistently show that the brains of highly educated, cognitively active individuals can contain just as much pathological damage as those of less active individuals. What cognitive reserve does is delay the point at which that damage becomes clinically apparent. In other words, it delays the expression of the disease, not the disease itself. This distinction has profound implications for public health. If the goal is to delay the onset of symptoms, then the most effective strategy is to build reserve across the entire lifespan, not to intervene only once symptoms appear. This shifts the focus of brain health policy from reactive treatment to proactive prevention. And it means that the most important investments are not in hospitals or pharmaceutical research alone, but in education systems, in the quality of working life, and in the social infrastructure that enables meaningful engagement across all stages of life. I will leave you with this thought: the science of neuroplasticity